So in this video I want to talk about a very interesting result by Alexander Skutin, which appears in 2013 issue of the Journal of Classical Geometry, Volume 2, 2013, and it's titled On Rotation of an Isogonal Point. Okay, so he's saying, in the short note, we give a synthetic proof to the problem posed by Arseny Akopian. We prove that if Poncelet rotation of triangle T between circle and ellipse is given, then the locus of the isogonal conjugate of a fixed point P with respect to T is a circle. So there's a beautiful proof. Highly encourage you guys to take a look at this paper. I'm going to leave a link in the description. But let's actually look at an illustration what this whole thing is about. Okay, so I'm going to switch to Mathematica. And what Alexander Skutin is talking about is the following. You're going to pick a circle-inscribed Poncelet family. For example, the one that we're showing here, this family of blue triangles, and you're going to elect a fixed point P on the plane. So I can place P somewhere on the plane. It doesn't have to be here. It can be outside the circumcircle or inside. It can be anywhere, okay? And the observation is that over Poncelet, the locus of the isogonal conjugate of P is a circle. So let's go ahead and draw the isogonal locus of P. It's appearing up here, okay? Let's go ahead and center this guy very well. And let's go ahead and animate the family now. So there you have it. This is the result, which is quite beautiful and harmonious. You have an arbitrary circle-inscribed Poncelet family, a fixed point P, and for every member of the Poncelet family, this is a blue triangle, I'm computing the isogonal of P with respect to the blue triangle, and it falls over here. Amazingly, over the Poncelet family, the locus of what I'm showing here as G, which just represents isogonal of P, amazingly, this locus is a circle. Now, this works even if I move P around, right? So I can place P anywhere. I can place P over here, and I can dynamically see what's going on with that locus as I vary P across the plane of the family. Of course, if P is going to approach the circumcircle, recall that the isogonal conjugate of the circumcircle is the line at infinity. So as I'm approaching the circumcircle here, my circular locus is becoming larger and larger, and when P is on the circumcircle, it becomes the line at infinity, which can be regarded as a degenerate circle, right? So let's go ahead and move out of the circumcircle, and I can see here that if P is out of the circumcircle, I'm still a circle. Okay, so that's the really beautiful result. That's a beautiful result illustrated in the video. You can see that the center is not necessarily an obvious location, and the jury is still out as to what are geometric properties of the center vis-a-vis, you have P, you have the center of the caustic, and you have the center of the circle. What if I pick a different pair of ellipses? I think I have a different pair of ellipses here. Maybe I don't. I'll circle it. Maybe I don't. Okay, so let's just stay with this one. Now, the purpose of this video is actually to extend this result to the situation when the arbitrary Poncelet family is not circle-inscribed, but it is ellipse-inscribed. So let's pick an ellipse-inscribed family, for example, this one. And let's, before we analyze the isogonal, let's just take a look at the scenery here. What am I talking about? In fact, I actually want a non-concentric one. So maybe this one. Yes. So here's a non-concentric pair of ellipses, non-axis aligned. So we're going to say that these are in general position. These are two nested ellipses. And again, I have a Poncelet family. Okay, and I have a fixed point P. Now the question now becomes, what is the locus of the isogonal of P? And it turns out the locus of the isogonals, let's go ahead and pick a, just for the sake of first set of explanations. It turns out that whichever P you choose on the plane of this pair of ellipses and in this Poncelet family, the locus of the isogonal of P is no longer a circle, but it remains a conic. So the special case where the outer ellipse is a circle will render the locus of the isogonal a circle. But if the outer is not a circle, the locus is a conic. Now, what kinds of conics can we have? Can we only have ellipses, or can we have the other two kinds of conics, parabolas and hyperbolas? And it turns out that depending on where P is, and we don't know what the specific rule is, this locus can, as a first property here, if P is exactly on the caustic, anywhere on the caustic, the locus of the isogonal will be an ellipse which is tangent to the outer ellipse. Okay, so we can see here that as I slide P on this inner caustic, I'm going to be visiting a family of elliptic loci. Now, very interesting question is, what's the locus of the center of these loci as P is slid in the caustic? Is this an interesting shape? We could investigate that. Now, if P is moved to, say, an intermediate location between the inner and the outer conic, I will remain an ellipse up until this ellipse, in fact, degenerates to a parabola right here, just about right here, and then it becomes a hyperbola. Okay, so now I'm a hyperbola, and in fact, as I cross over through the boundary, I become an ellipse again. Okay, so there's a region here which is poorly studied, over which, let's go ahead and show this hyperbola by scaling it out, over which my locus is a hyperbola. There's a region. There's a region over which the locus is an ellipse. There is a one-dimensional boundary where the locus is a parabola. Okay, so if I move again this guy towards the center, there's going to be a particular position right about here, okay, where I'm a parabola, and there's actually a 1D locus of P where this guy is a parabola. Now, the other very interesting remark is what happens when P is exactly on the boundary, when P is exactly on the outer conic. And then you get this really neat result, which is a generalization of Skutin's result, which is the following. If P is on the outer ellipse, the locus of my isogonal conjugate over Poncelet is actually a straight line. So for the special case where the outer ellipse is a circle, this straight line is actually the line of infinity. So if P is on the outer conic, when it's a circle, the isogonal conjugate is going to lie on the line of infinity, and the line of infinity can be regarded as a circle as well. Skutin's result is that it's going to be a circle for P placed anywhere, but that's a very special circle. Now here, if you actually relax the condition that the outer conic be a circle, you get this really neat result that the locus of the isogonal is a straight line, and if I slide over all possible positions of P on the boundary, you're going to be spanning a family of straight line conics, whose envelope I haven't yet analyzed. This could be actually a very interesting envelope. I don't know if this envelope is going to be a conic or or a circle, or it's going to be a non-conic. I would hazard to say it's going to be something interesting, such as a conic or a special conic, such as a circle. We can try to eyeball that, and I haven't implemented the calculation of this envelope. Of course, as P is going through the circumcircle of the current triangle on the screen, G is going to explode, right? So there's some positions here of P, or likewise of the Poncelet orbit, where G is actually at infinity, and that happens when the circumcircle of the blue triangle, not shown, passes through P. So it's going to be, I don't know, 4 configurations of this family of triangles when this is true. And likewise, if I'm actually moving P around, there's going to be moments where P is actually on the circumcircle of the shown triangle, and there's going to be some instability in the calculations. Okay, so this is a result I wanted to share with you guys as a generalization to Skutin's 2013 paper. See you on the next video.